And as a person who spent the last 15 or more years in doing essentially what is today called DevSecOps, I was always looking at simplifying things. And especially when you are dealing with a pretty large project where you have tens or hundreds of servers, especially deployed to the cloud, sometimes there are, and I'm sure you've seen this many times, sometimes there are tasks that initially look kind of secondary. So essentially like deploying transport encryption between servers, between a database, the application server, on all the things that we are bugging the developers and architects during a penetration test, during infrastructure vulnerability threat modeling. And suddenly, this kind of secondary tasks, they start to grow up, because when you start to deploy TLS between your database and application server, you suddenly discover you have to set up the PKI infrastructure for that purpose. And this presentation is exactly about how I dealt with this problem, because this is, indeed is frustrating. And in most cases, I've seen, and I actually worked in, this problem was delayed. And this is why what essentially this slide is about. We just push this forever until we have to go through some kind of third-party compliance audit or penetration test, and then in panic everyone is patching all these TLS connections between components just because we didn't really think about this before. So I was wondering, is it possible to kind of do something in a way that will be not so intrusive? Because TLS is definitely intrusive in this sense. That's something that will be just there, protecting your traffic, but will not really require so much work. And this is essentially why I started doing this work, and it seemed to work. Actually, it was pretty good success. And this actually originated from times like in late 90s and early 2000s when I was working for a company designing an IPSec encryption gateway for sensitive traffic. And it was using IPSec. And I will be talking about the protocol itself more, but this is how I kind of was first contact I had with IPSec, and this is how I knew it existed. And I knew the internals, which allowed me to do the thing I wanted to do now pretty easy. So, transport encryption, we are on a security concerns, and I don't need to explain in details why we need that, but this is essentially what you see on a typical traffic between a application server and database. This particular traffic is it's from between an application server and something, probably a cache request to Redis. This is from my application, actually. I just captured the real traffic to be easier. This is, you see here, it's a Redis password. It's from UAT, so it's not really sensitive, and I changed it afterwards. But this is essentially what you can capture in a live traffic. And this is again SQL query which I made up, but this is not. This is quite realistic. So even especially if we have cloud infrastructure, because if you have your own servers inside your trusted network, I mean, who cares really? Because we are not really dealing with threats like someone plugging a sniffer probe into your local network. But if we have cloud infrastructure, we don't really have guarantees that the servers will be even if the same network segment, not to mention that they will be actually in the same geographic data center. So your traffic that you see two servers sitting in the same kind of group in a cloud environment, they can be actually placed quite distant, and your traffic may be even running over the internet. So this is essentially why we are bothering ourselves about the transport security. And what choices we have? There's a lot of them. I will be not talking about them in details, but the parameters I was looking at is performance. So is the tool, is this mechanism implemented in the user mode? So is it essentially a part of an application, like we have PostgreSQL implements TLS, it's using the OpenSSL library, it's all running in a user mode, so essentially in the user space in the operating system, or is it running in a kernel? So IPSec, and this is huge advantage, and it's very beneficial for the performance, runs as part of the kernel, essentially. This is the only solution that actually runs as a part of the kernel. The other one that I have recently found is WireGuard, which is a very interesting project that could be potentially replacement for IPSec in future, that actually resolves plenty of its deficiencies. Unfortunately, if you look at, realistically, if you start deploying these things on a, real-world environment, and you look at the distributions, the Linux distributions that you have on cloud environments, it's not always there. It's available as additional kernel modules which you have to compile in, and this is a no-go on most such projects, obviously. With other projects like that, there's a lot of OpenVPN thing. I won't be even going through them in detail, but because we don't have much time, but they all have deficiencies, which you can ask me later on, but there were bugs in them which kind of disqualified them from my point of view. And TLS, so essentially using built-in support for TLS in databases, in web application servers, etc. This is the kind of main alternative that I'll be talking about. And the main problem I have with the TLS is that when you're setting this up in a real application stack, there's so many formats for configuring the TLS parameters because every application has its own format, and it's very, very confusing, even if you are using some kind of a configuration management system. And it's essentially error-prone, so you can make mistakes. And there's so many of them. This is MySQL, this is PostgreSQL, Redis doesn't even bother about TLS. This is CouchDB. This is Welcome Erlang. This is RabbitMQ. This is High HA Proxy. And then when you start, again, deploying the certificates, it's an overkill, really, because the whole PKI infrastructure was designed for dealing problems at completely different scale. The PKI infrastructure wasn't really designed to deal with encryption or authentication between 10 servers on a cloud. It was designed to deal with authentication of thousands or millions of entities on the untrusted network like internet. So when we are trying to deploy the TLS certificates, and I'm sure you've been through this pain many times, it's real burden. And there is essentially so much things you have to do. You have to be careful about deploying the certificates, the keys and everything. It's just annoying. And then TLS protocol, it gives you a lot of choices. This is all the configuration parameters for typical OpenSSL, OpenSSL support. Some are strong, some are weak, some you can use, some you cannot. And essentially, especially if you are trying to speak to an older implementation, you may get this. So essentially, you are trying to be the best, the best practices, staying on the bleeding edge with encryption protocols, but then you hit some old crappy implementation and you have to support RC4, for example. And then our services, we just cannot work over TLS because TLS is TCP, and these services are like UDP or DNS or like syslog or DNS. They are just working on UDP by default. And obviously, you can implement syslog over TLS. There are solutions for that, and the same for DNS. But this is, again, kind of trying to squeeze an existing solution like UDP with all its advantages into something else because the tool that you are using doesn't really support the original protocol. So this is the things I didn't like in TLS, and this is essentially what I was trying to get rid of. And on the other hand, IPSec is a protocol that has been with us for almost as long as SSL. The first version was released in '95. The work on IPSec started much earlier. It was like at least 5 or 10 years before. It was started by NSA and this obviously brings a lot of bad associations, but IPSec is one of the protocols that has been probably most audited over the time. And as you can see, there were so many releases of SSLs and TLS, all of them fixing really fundamental bugs, and there was plenty of implementation vulnerabilities on the way as well. On the other hand, in the IPSec world, not much, the changes, there were a lot of changes, there were many features being added, like for example, NAT traversal, which, sorry, still recovering, like NAT traversal, which originally wasn't supported by IPSec by the first releases, but the changes were not so revolutionary and not so fundamental. So you can see that the kind of cryptographic base of IPSec, they were sound from the very beginning, and this is and there were much fewer implementation vulnerabilities as well. So attacks like crime, beast, and everything, they just don't apply to IPSec. Unfortunately, one thing happened with IPSec. I'm trying to present IPSec as simple, and it is really simple if you use it in a simple environment, like a simple scenario as I am trying to show you. However, IPSec is incredibly complicated, especially because it's using really weird terminology. So the RFCs for IPSec are full of really bizarre names, like really simple things are called security associations, etc., etc. It's a completely different language. There was a kind of trend back there in the 90s that if you design a new security protocol, you have to invent your own language. And this was essentially the problem with IPSec back then. When I was reading the documentation first time in the 90s, I was like really close to really getting crazy, because it was really, you have to reset your thinking completely and adapt to the language from the very beginning, from the very basic concepts. If you look at this, in hindsight, it's really easy. And I will try to show it the easy part. Unfortunately, by now, IPSec is mostly known by probably VPN users, Cisco users as a VPN protocol, which was back then completely secondary function for IPSec, the tunneling of other protocols, because IPSec was intended to be used as the basic encryption protocol for end-to-end communication between all hosts on the internet. Unfortunately, for many reasons, this kind of functionality was abandoned, and we can only now use IPSec for functions like I'm just describing, or for VPN purposes. So essentially, how does IPSec look like in real life? So you got typical, spaghetti of TCP connections between two servers. When you enable IPSec between two Linux boxes, you got all this nice and elegant ESP packets, which is ESP's encryption security payload, which I'll be talking in detail in a second. All is encrypted, and you can actually look inside. This is typical encrypted traffic, and sorry, unlike in TLS, you will not see the whole dumps of PKI certificates in the traffic, host names, etc. There's some exceptions for that, but that's for special occasions. The IPSec architecture, it's really simple. There is ESP encapsulation security protocol, which is essentially the bulk workhorse that does encrypt the actual traffic. It's an IP protocol, and I'll explain on a network stack what it really means. It lives in a kernel space, and once you configure it, it will just encrypt all the traffic that you tell it to encrypt, and that's really it. You just forget about it. It lives well below TCP or anything like that. And then for keying, for essentially actually establishing the authenticity of the communicating servers, and for exchanging keys, you got the iKey, Internet Key Exchange Protocol, sorry, which works on port 500 UDP. Implementation-wise, it's implemented by a very small footprint Rekeying user space, this daemon that just sits in the memory and talks to the other hosts. So just kind of reiterating, you got two hosts, host 1, host 2. They got a lot of services. The services talk to each other. Each of them establishes their own TCP connection. Then on the top of TCP, they establish TLS. Each of them uses their own session keys and everything. Each of them runs the quite expensive RSA or elliptic crypto exchange for their own connection and maintains their own state. And there are services which do not run TLS because they cannot, because they run on UDP, for example. In ESP, IPSec-based stack, you just establish one connection, one ESP. I don't want to say tunnel because it's not a tunnel, but one ESP kind of connection between the two hosts, and you just forget about everything else. All the hosts communicate using regular TCP or whatever the protocol they speak, and that's it. Everything is encrypted by automatically. So essentially, if you look at the network stack, this is IP header, and then over the IP header sits the ESP header, which essentially contains some parameters like the encryption channel number, and everything inside is encrypted. And on top of that sits TCP, HTTP, and whatever protocol you are using. Now going to how you configure this. Again, this looks very complicated, but it's really, really simple. You got two kind of kernel structures that hold the data. One is SPD, Security Policy Database, and it contains statements which essentially say you must encrypt traffic from A to B. You may encrypt and compress, if possible, the traffic from A to C, and the traffic from A to D just goes in plain text. It's like a routing table, except you don't point to the destinations. You just tell the kernel what to do with the packet in terms of cryptographic transforms. So the next structure in the kernel is Security Association Database, which essentially says, okay, I have to encrypt traffic from A to B. So SAD tells you how to do this precisely. Essentially, what key I use for encrypting traffic from A to B. And because every security association has only one direction, from A to B, you have to have encryption rule from B to A. So you have two rules for every host, essentially, that you want to speak to. Typically, in modern Linux systems, two algorithms will be implemented in most systems. So this is the safe default, which are pretty decent from security point of view. The SAD will also contain the unique kind of identifier for every connection and a ton of other parameters which are not really very important. How you configure it? There's one simple command, IPXFRM policy, which shows you this policy, which essentially says this is a V6 address. From this V6 address to this V6 address, all traffic has to be encrypted using ESP in transport mode. And okay, this is not a requirement, this is a suggestion. So if you say use, essentially means you can encrypt but don't have to. There are two commands for that. One which is kind of new style. This one is the old style. It provides slightly more information. The same commands are used to look at the Security Association database, and here you actually can see the actual encryption keys. This hex string is a raw key that you use for encrypting this traffic. And you can see these two rules. One is from this host, let's say this is A to B, and again, a reverse traffic from B to A. How we configure it on a regular Linux system, there is a file, etc IPSec tools conf, and I'm only showing this for you to know, to understand how you configure it, how you can look at the configuration, how you can experiment, how you can edit it. But normally, you don't want to configure this by hand. because it's just I'll go into details later on, but it's very repetitive process and it's prone to errors. You just load this policy using the setkey commands with, and this is something that you essentially say. So all these decisions, traffic from A to B, this is your decision. You make the policy and you set this in the file. While the actual encryption parameters, they can be set in two ways. One of them is manually, so you just actually configure the raw keys. The other one is using the ikey daemon, which is much easier and much safer for many reasons. Normally, the easiest way to use Raccoon, the ikey protocol, is to use pre-shared keys. And this is the great simplicity in using IPSec. You no longer have to manage the whole PKI infrastructure. You can just use regular pre-shared keys, which are set in for every single pair of hosts that communicate. However, if you have something like 100, 200, 1,000 hosts, in this case, the number of the pre-shared keys you have to manage and generate will be quite significant. So this is exactly where PKI can help, actually. And you just set up a PKI certification authority, and you just deploy the keys. This is the scaling, in this case, may just make more sense in this case. The configuration file, IPSec tools conf, this is actual policy rule. As you can see, what it says essentially, add to security policy from host A to host B. Any protocol, this is out traffic, so going from the host, use IPSec encryption with ESP protocol. And this is all it says. What is also important at the end, it says, just try to point it. It says use. It's an optional. So if there is no encryption rules set for these two hosts, you can send the traffic in plain text, which is a bit safer from testing point of view, but obviously not so good from confidentiality point of view. Raccoon conf, again, I just wanted to show this as a reference, but there's nothing you need to significantly edit in this file. It's just a set of rules that inform the Raccoon what hosts it should be expected to talk to or receive connections from. So what are the kind of hosts that will be trying to establish keys with us? What you can do in SPD is much more than that. It's just very simple configuration. You can exclude specific traffic from encryption. You can drop traffic even. You can do a lot of things in security policy database. It's just advanced use, essentially. One thing that is interesting and useful, you can enable compression as well, which is kind of, you can stack this transformation. So one transformation may be compression, which is completely transparent and doesn't provide any confidentiality. And that on top of compression, you encrypt the traffic with ESP. And the pre-shared keys, it's just the host name that you want to talk to and the pre-shared key for this host. Obviously, on both ends, you need to have the same pre-shared key. And if this looks complicated, I just wanted to show you this file so you don't really feel kind of surprised that they have very kind of unusual syntax. In reality, you don't really have to touch this files ever, because all this configuration may be generated automatically. I will be showing this later on. Essentially, what happens when you start this Raccoon daemon, this is a typical message. It speaks to the other hosts, establishes the keys, and that's it. And you can see this probably once a day, because it will be rekeying the existing session keys automatically, depending either on the traffic or the time that has passed. What essentially happens behind the scenes, when you define the SPD, the kernel will look at the SPD table, and it will, when it sees traffic that falls into the policies. So essentially, we said we have to encrypt traffic to the host X, and kernel sees the traffic outgoing to host X. It will look into the SAD and look if there is any encryption rules for this particular host. If there are, they will just send and encrypt it. If there are none, it will speak to the Raccoon daemon automatically, and it will establish the keys. There will be like a 2 seconds delay approximately, and then it will continue the traffic. And again, next rekeying will be probably in a few hours. So it's very, very rare process. What you need to open on the firewall is just two things: protocol ESP, which is protocol number 50, and for the iKey protocol, it's protocol port 500 for UDP protocol. That's it. Syntax for NF tables is even simpler. As I mentioned, Raccoon will do rekeying periodically for you. So this is good from security point of view. You don't have to worry. It's just built in as part of the protocol. And I'm mentioning this because the IPSec connections are long-term. So essentially, you can have an IPSec connection that will be last for, days or months. You don't touch it. It just refreshes itself automatically, and you just don't have to really think about it. The IPSec compression, IPCOMP, I try to show you the difference if I'm hitting the right line. Essentially, this is the traffic from dev0, so easily compressible traffic, and you can see the size of the packet is 100 bytes. So if you send your random data, which is not compressible at all, the packet size is over 1,000 bytes. Essentially, you have 10 times reduction in size if you are using compression on easily compressible string in this case. So it's definitely worth using if you have a textual protocol like SQL, for example. For some protocol, it will probably just increase the processor load without any benefit. If something is not working, and things may be not working, these are the tools you want to use for debugging things. The best friend is definitely tcpdump, because you will see whether the traffic is encrypted at all or not, and what is really being sent between hosts. Typical problems that I have seen during configuration of IPSec between hosts is essentially when you don't have entries in SPD, which may be caused by syntax error in the configuration files. There may be IP addresses that are mistaken, so it will not catch the right host that you are trying to protect. Or the set key was not really called after reboot, and this is done different on various distributions, which you may get a situation where either the traffic is unencrypted completely, or you receive traffic that is encrypted, and you are not expecting this because you have not set up the policy rules for that. When the SAD is not populated, which can be caused, for example, by the Rekeying daemon not running at all, or it failed to establish the keys with the other host for many reasons, or you have actual key mismatch. So you set one key on one host, and on other host you have set another key. Essentially, you will also may see no traffic, encrypted traffic coming to your host, but not being decrypted because the kernel cannot decrypt it. Other typical issues is essentially when you have not opened the ports on the firewall, you will see different strange things like traffic is coming, you can see encrypted packets, everything is set up correctly in SAD and SPD, but the traffic is not getting through. Very common reason is just not opened the right protocol on the firewall. Another very common issue, which I made a lot of, spent a lot of time debugging when I made some mistakes, is asymmetric mismatch. So essentially, you have configured IPSec on one host in require mode, you have not configured it on another host, or you have flushed it, cleaned the tables on one side, and they are still there on the other side. And essentially, the kernel cannot make sense of it. Also, if you use in tunnel mode, you may want to reduce the MTU because there's small overhead. But again, All these things are very rare, and if you deploy, you can also have some issues with Raccoon. But again, as I mentioned before, these problems are not really that common. I spent a lot of time debugging them because I was writing this Ansible role for IPSec, and because this IPSec configuration is repetitive. It's not a problem with IPSec. It's just how the whole process works. It's very prone to mistakes, to typos, to misconfigured IP addresses, etc. It's very inconvenient to write it by hand. So, on the other hand, it looks perfect, like a perfect task for configuration management like Ansible. And this is precisely why I have written this Ansible role, which is available on GitHub and on Galaxy as well. By setting a few simple parameters, like the one that is really necessary is the IPSec secret, which is kind of your master secret that you use for all the other hosts. You can automatically deploy IPSec to all group of servers. Like you have a group in your Ansible inventory called IPSec. You have 10 hosts by just one run, and if you have time, I can actually show you this in action. You can configure this host, these 10 machines, in a matter of a minute to use IPSec immediately in transport mode very efficiently without any hassle. There's a few options which are explained in the documentation that are rarely necessary. What this Ansible role really generates is this configuration file, IPSec tools config, which, as you can see, writing this by hand is a nightmare because you have to remember about switching the directions of the tunnels, you have to configure all these options, etc. Ansible does all this for you, and this is an ideal tool to do such a repetitive task in an efficient way. The keys are generated. Probably that's something, if we are on a security conference, that's something we should probably discuss in detail. In a very simple way, because we are working in a, obviously the best way of doing this would be to generate them in a completely random way. However, we are living in an Ansible world environment here. And every template has slightly limited way of interacting with the others, understanding the state of the other host. So we are generating the keys in a deterministic way, but still it's secure. So essentially for iKey, so if you are just using the Raccoon daemon, the only thing the Raccoon needs is a shared secret between two hosts and nothing else. Everything it will deal with automatically. So we just take the secret, concatenate it with names of the two hosts that are kind of connecting, and we hash it. And that's it. This is the secret. The secret obviously never leaves the deployment machine. It's never present on the target server. It's always there in the hashed form. In set key mode, it's slightly more complicated because we have to actually generate the actual encryption keys, down to the hex string for authentication, encryption, and then we have to generate the identifiers, all manual, so it's slightly more complicated, but it's exactly the same principle. So the good thing about using Ansible for this purpose is the runs of Ansible playbooks are atomic. So you won't end up in a situation where you have two hosts partially configured. One of them is configured, the other one is not. If you run your Ansible play completely and it will run successfully, you'll always end up with 10 hosts that are either without IPSec or with IPSec. All of them, they have the same configuration for IPSec enabled or completely disabled. Obviously, because the kind of the master secret that we are keeping in our configuration variables on the deployment host is a secret. It should be protected. Obviously, we should be using HashiCorp or Ansible Vault, which I'm using personally, or any other proper secret management solution. And If you have any questions, just feel free to shoot. I'll try to demonstrate how it actually runs on a live environment. So this is two Ubuntu boxes on cloud. This is one of them has a sniffer running. This is the same machine where I will open a server using Netcat. So I'll just move it to the top of the screen. This is Netcat listening on port 31337. And I don't remember what kind of policy I have loaded on these machines right now, but we can see this on sniffer. So essentially, we are sending etc password file to the other server. And it's gone through very quickly. And we have received, actually, what we received is a plain text traffic. So no policy is loaded at this moment. Oh, this is probably better from the, it's more, you can see this slightly more. This is regular TCP unencrypted. All the packet internals are plainly visible. We go to my deployment machine. This is the previous run of the play. And the file with the configuration variables, it really, the only option that is really necessary is IPSec secret. And it's a long string, as you can see, was generated using OpenSSL run. It's completely random. These options are not required. I'm just using them so I can switch the modes, different modes for the purpose of this presentation. So this right now, the IPSec policy is disabled, which is essentially kind of an automatic kill switch. I'll delete this line completely, so the default configuration will be restored. And it's running. There's a lot of steps being done in the beginning. Essentially, it's installing ensuring all the packages are installed. Raccoon is installed, IPSec tools are installed, etc. And that's all. What is really critical is this line. This is where the actual configuration is being generated. And if we go to the server, this is what was just generated. And as you can see, this is configuration for the actual encryption tools, encryption parameters and everything. We can have a look what I did. The IPSec mode I have set is manual keying, which is kind of slightly more complicated from the configuration point of view, but we don't really care because all is generated automatically. And now we have sniffer running. We can rerun the server, the netcat. We send the data, and as you can see now, it's all ESP packets, so it's all encrypted. And this will be continuing forever, essentially, as long as the policies are enabled. OK, we can try to change it to even more default policy, which is using Raccoon daemon. So we delete the IPSec mode parameter, rerun the policy again. Sorry, rerun the play again. In the meantime, I will rerun the server. Let's have a look here. There were more changes because now the play has actually not only configured the IPSec configuration, but also Raccoon configuration. So this is Raccoon service, Raccoon pre-shared keys, Raccoon configuration, etc. And if we go to the other server now, it has been sent. And what you can see here is IPCOMP, which is actually the older name for iKey protocol. So what has happened, the protocol is currently running in use mode. So there's no requirement to use encryption. So if we scroll up, we can see that the actual file was sent using plain text TCP. And you can see this TCP, the plain text packets here, because we told it that we do not require encryption at this moment. However, if we send it next time, it will be encrypted because during the first run, there was no existing encryption configuration. So the kernel said, okay, I'll tell the raccoon to establish the connection, but because I was told I can send it file in unencrypted, I'll just send it as soon as possible. In the second run, we already had an existing encryption configuration, so it was just sent using this encryption configuration. If we want to prevent any unencrypted traffic from running, we would set IPSec policy require let's restart the server. And because each run will flash all the configurations, so we will be dealing with a fresh start. In this case, okay, let's scroll a bit. Let's run it. You see there is a slight delay, about 1 or 2 seconds, and this is where the kernel holds the TCP transfer, because at the same time in parallel it's talking to Raccoon. Raccoon is talking to the other host. They are exchanging the keys, and once the configuration for encryption has been set, the kernel goes on with sending the traffic. And you can see these encrypted packets here. And at this point, you can send any traffic. It can be UDP, it can be TCP, all kind of exotic protocols that are not neither TCP nor UDP. Everything will be encrypted. Essentially, everything that you set as requirement for encryption. You can make exceptions, obviously. So if you look at the Ansible role, by default, it will exclude ICMP, and it will also exclude SSH. So you can SSH between the two boxes, even if you misconfigure the IPSec configuration. That's it. I'm using this solution on all my servers, on my server farm for the last year or two, and it's been just there. And that's it. Thank you very much. I don't know if we have any time for the questions. Yeah.
Have we got any questions?
I don't really see because the light is very strong.
Yeah, I'm not a networking guy, so this might be a dumb question, but if you're encrypting all the traffic at that kind of layer, do you have any kind of mechanism or facility for inspecting traffic as well, if that's something you want to do, like effectively manning the
yeah, that's you touched a very important point, how you make sure that you are actually encrypting the traffic. Because this is a very good point, because I have seen situations where I deployed policies like that, and then for a week I was certain that the traffic is running encrypted, but it was not. You can do this in many ways. So one of the ways is just to set up firewall rules that will warn you about any TCP traffic or UDP traffic leaving your machine. Essentially, if you set up ESP, there's no TCP or UDP traffic leaving your computer. So it doesn't have to be blocking rule. It can be just a logging rule, so you can see that there is some unencrypted traffic leaving the machine.
That makes sense. I was also thinking about it along the lines of like NIDS type of facilities where you want to actually inspect the traffic for signatures or whatever else for intrusion.
Oh, you mean okay, like IDS probes, for example?
Yeah, if you're able to use that, you can.
I mean, to some extent you can, because if you know the keys, you can. So in the manual encryption mode, you can definitely decrypt the traffic. You know the actual keys, and if you run Wireshark, for example, Wireshark, and I guess most of the commercial probes, they also can decrypt the traffic if they know the keys. Otherwise, I have not really thought about this. I guess you would need a separate tab that sees the unencrypted traffic.
Got you. Thanks.
So I have another question.
Yeah.
In a regular TLS setup, I would have something like certificate revocation lists if keys got leaked. What would be the equivalent here? Do I just run the Ansible playbook again? If
you
one of
mean
my
what?
keys get compromised?
Oh, okay, CRLs. Well, if you are using Raccoon with TLS certs, then you just use the regular CRLs.
Oh no, I meant in
But
set key
if
mode.
you run pre-shared keys, then essentially the solution will be just to rerun with change master, I guess.
Okay.
Actually, if you this would be only the case, really. I'm just thinking about scenarios. If you have someone who broke into your server, one of the servers, but even then, they will be only able to see the traffic from this server. They will be not able to see traffic between any other servers because they are using completely different keys. So only the machine that was compromised would be compromised. And if you are on the machine, you got root, you don't really need to decrypt the IPSec to see the traffic, right? But in a general case, I would say changing the master secret and rerunning the role would be the solution. It would be pretty quick.
Okay.
Thank you. All right. Thank you very much.